guys, welcome to the second lesson of complex numbers. This video is going to cover exercise 1b, quadratic equations. So first of all, we're going to have a look at quadratic equations with real coefficients. And when you're solving quadratics with real coefficients, it may involve any of these following methods. So you might need to complete the square, or use sum of two squares, or use the quadratic formula. So I'll show you an example of using each method. The first question is to solve x squared minus 4x plus 13 is equal to 0. Let's try and solve this using completing the square method. So using the first two terms that contain x, I can complete the square by finding the constant that is needed to make it a perfect square, and in this case it would be a 4. Now at the same time, I might just move the constant 13 to the other side and also add 4 because I've added 4 on the left hand side. I gotta do what I've done on the other side as well. And that leaves us with x minus 2 all squared is equal to -9. And of course with real solutions we weren't able to find the answers to x, but because we're dealing with complex numbers we can now find the solutions. So we can just square root both sides as it is, and we get square root of -9, but we need to note that root -9 can be written as root 9 times -1, which can be separated into 2/3, and we can write that as 3i. So I'm going to rewrite the solution as 2 plus minus 3i. For the second quadratic equation, find imaginary solutions to z squared plus 10 is equal to 0. Now for this one, because I've got the sum of two numbers, I can use sum of two squares to rewrite the equation, or I should say factorize the equation. So remember that if we multiply two conjugates like this one, we end up getting the sum of the squares of the coefficients. So using that, I guess we're going backwards in this case, I can say that this is x squared and this would be my y squared, and we can refactorize it as z plus I root 10, because if that's my y squared, my y would be root 10, and then I just write the conjugate down. So the second bracket would be z minus I root 10. And if that entire thing is equal to 0, we can simply solve for z as plus minus I root 10. The third example, I might just use the quadratic formula for this one, although I'm happy for you to use the other methods. I'm just trying to use different methods to solve the problems. So if I just plug it into the quadratic formula, and I think by now you have memorized the formulas. And then if I simplify the third, I get a negative number inside the square root, but no worries because we know we can pull out the root 64 as 8. Would still have the -1, but how about I just write that as I on that step. And then I can simplify the solution as minus 3 plus minus 4i. So you can just directly plug it into the quadratic formula and just replace the root -1 as I. Now an important thing to remember, for quadratics with real coefficients, we actually have the complex solutions occurring in conjugate pairs. And you can actually prove that quite easily. Feel free to pause the video to go through the proof yourself, but yeah, here goes the proof. So first of all, I'm gonna define the context first. So I will let a polynomial equal to a generalized quadratic and I will let it equal to 0 and have a solution named as Z. It's pretty common sense, but I'm just gonna state that the coefficients should be real in this case. And saying that Z is the complex solution of that equation, I am saying that if I plug in the root into the polynomial, I should get 0. Now what we're going to do next is we'll try and take the conjugate of each side. And if I directly apply the conjugate, it should look like this. But having the conjugates on the real numbers, it's actually itself, because remember, conjugates are meant to be changing the sign of the imaginary part only. So I could probably rewrite that like this. So all the real numbers don't have to have the bar on top of it. And I can rewrite this expression as this. And by rewriting the equation like this, it tells me that plugging in Z bar, so the conjugate of Z, is also a solution because it equals to 0 when you plug it into Px. So I could say that P of Z bar is also equal to 0, meaning that Z bar is also a solution. And just note that if the coefficients are not real, then that part wouldn't really work. So this would be only true for quadratic equations with real coefficients. Let's try the next example. So the question goes, find the quadratic equation with real coefficients given that one of the roots is 5 minus I. Well, since we're given that the equation has real coefficients, we can use the identity we've learnt above and say that its conjugate is also the root. So let me just write that down. So since real coefficients, the conjugate of W is also a root, which means I can construct the equation again by taking the difference of those two roots. So the conjugate of 5 minus I, of course 5 plus I, is equal to 0. And you could just expand it however you like, but I think, okay, let me just expand out the negatives first. Because the benefit of this expression is that I can actually rearrange or regroup them as this. Then I actually get another expression of conjugates. So I can use the sum of squares to expand it out as a squared plus b squared, which is just 1. And I can just expand and collect like terms. Ta-da. Now, the box below, I haven't proved it, but it's actually quite simple to prove. It says a quadratic equation with real coefficients, which has this root. The equation can be constructed like so. If you generalize the expression for Z and actually try it out yourself, you'll see that the proof is not too difficult. So this one, I will say, you try yourself. Try, prove yourself. So give it a go and let me know if you have any questions regarding that. Okay, now let's get on to the equations with complex coefficients. But before that, let's simplify down the concept a little bit and let's have a look at the square roots of a single complex expression first. So if we want to find square roots of a complex number, what we do is we let the square of the complex number expression equal to that complex number and solve for x and y. And to do so, you can use a sort of like a formula way by generalizing all the expressions. So starting from this method, we can expand the left-hand side to get this expression, and we can equate the real part and the imaginary parts, because if we are saying that these two expressions are equal, then we should have the real parts, so the parts without the I, equal to each other, and the part with the I equal to each other as well. And that's what's written here. So whatever question you work with, if the question asks you to find the square roots of the complex numbers, you will always get down to this step. But my recommendation is that you don't just go to this step straight away, but define this and then expand it and then derive this. So please derive it every time you solve these types of questions. So I'll show you an example. If the question says, find the square roots of 7 plus 4i, then I'm going to first define what I'm using. So let this complex number squared equal to 7 plus 4i. That means if I find the expression for x plus iy, that would be the square root of 7 plus 4i. But if we expand the left-hand side, we get x squared plus 2xyi minus y squared is equal to, oops, whoa, I miswrote the question. My bad. This is meant to be 24i. Well, no wonder why the numbers didn't work out. So if I let it equal to 24i, then now I can equate the real parts and the imaginary parts. So the parts that don't have I in it, the real parts, those expressions should equal each other. And the parts that contain I in them, of course only the coefficients of them, I can say that 2xy is equal to 24. Now at this point, I could probably just simplify this to xy is equal to 12. And if you can solve it by inspection, you are allowed to do that. For example, if xy is equal to 12, I'm thinking of factors of 12 obviously, so that this equation is true. So you can try out 12, 1, 6, 2, 4, 3. If you try 4 and 3, 4 times 3 is equal to 12, but also 4 squared minus 3 squared is 7. So if that works, you can just plug it back into the formula. And just note that if 4 times 3 is equal to 12, got to remember that -4 times -3 is also 12, as long as the signs are the same, right? And if you square it and take the difference, it results the same thing. So I have two possible options. My square roots are either 4 plus 3i or -4 minus 3i. So the signs should be the same in order for their excuse me, in order for the product to be a positive number. Now this was a nice case, but sometimes the values of x and y cannot be solved by inspection, and in that case you're just going to have to solve it simultaneously, but using the sum of squares it might be just a little bit easier to solve. So let's try this question. Find the two square roots of -4 plus 2i. So starting with the same method. Always start the same. Oh, minus y squared. And then if you expand it to equate the real parts, you'll get this and this. Now at this stage, you can simplify this to xy is equal to 1, but if you think about factors of 1, there's not many options, and it doesn't work to solve it back into that equation. So this would be the case where you can't really solve by inspection. And in that case, you can rearrange these, plug it in, and solve the quadratic. But as I said, there is an easier way. I might write this on the side, but if you think about squaring the sum of the squares, you get x to the 4 plus 2 x squared y squared plus y to the 4. The reason why I'm doing this is because I know I can write that as a minus 2x squared y squared in the middle, and I can just add in 4x squared y squared to make it equivalent, and this first three terms, those will be factorized to the square of the difference of the square numbers, and 4x squared y squared is also a square of 2xy. And hopefully you now see the reason why I've done that, because that expression can be written as this expression and this expression, which are the expressions that we get in the equation, and we need to solve that simultaneously. So using that identity, I could come up with the expression for x squared plus y squared, because then that would be just the square root of this squared plus that squared. And as a result, I get 16 plus 4 root 20. I'll probably simplify that to 2 root 5. And if those are my equations, I can use this one and this one to solve for x and y very easily. Because if I add those two equations, I would get the y eliminated, and I get 2x squared is equal to negative 4 plus 2 root 5. If you divide both sides by 2 and square root it, you get x is equal to plus minus 2 root 5. And similarly, I can do equation number 2 minus equation number 1 and eliminate the x's. And now I'm going to get 2 y squared is equal to 2 root 5 plus 4. And again, dividing both sides by 2 and taking the square root, I would get plus minus root of root 5 plus 2. And plugging it back into x plus iy, I should be able to get the final solutions as plus root minus 2 plus root 5. I think it's easier to write than read. And the negatives. Oops. Minus I root 5 plus 2. And just note that I've only got 2 solutions, not 4. You might think I must have 4 because you've got the plus minus here and plus minus there. But go back to the identity here. It says 2xy is equal to positive 2. So we have to make sure that x and y have the same sign. So either both positive or both negative. Whew. That was it for exercise 1b. So feel free to go ahead and complete those questions. And let me know if you have any questions via email. Good luck!